All right, so this is looking at chapter 7. We're going to start chapter 7 this week. And this is kind of like the last main unit of the year. We have chapter 7 and chapter 8 kind of put together, and it's all about exponential and log functions. So we're starting off, it's kind of following the same pattern we've done through the year. So we started off looking at functions, and then we'll do some calculus with that functions. So at the beginning of the year, we looked at polynomial, rational, and radical functions, and then we did calculus with it. And then we did some trig functions, and then did calculus with it. And now we're going to do exponential and log functions as kind of like the last major function family, and do calculus with it. Exponential and log functions tend to be very, very useful in the real world. It models a lot of things that happen in real life. For example, right now, when we look at COVID-19 spread and the growth in those cases, you hear a lot of people talk about exponential growth. And so that's something we can look at using these functions and think about what that means and what that looks like mathematically. So to start off, we'll look at some vocabulary related to this, and then we'll go into looking at what the equations look like and what the graphs look like. So vocabulary-wise, there's these things called algebraic functions and transcendental functions. So let's say actually with the transcendental function, because that's a new word too, transcendental. And basically what that means is these are functions that can't just be written as a bunch of additions or raising to the powers. They need something else that's also happening with it. So these are not combinations of plus, minus, right? So you can't just create these using these operations, these algebraic operations. So things like trig functions, you can't get to sine, cosine, and tangent using just plus and minuses. Now there are ways to approximate it using pluses and minuses, but the actual function itself doesn't have that. So trig functions, and then log functions and exponential functions. Algebraic functions are things that aren't transcendental. So things like polynomials, rationals, radicals, right? Things that have, you can create these just by adding a bunch of things together or multiplying a bunch of numbers together. So we're looking now at transcendental functions, and really this whole semester we've looked at transcendental functions because we looked at trig, and then we've looked at, now we're looking at exponential and log functions. So we'll start off looking at exponential functions and work with them a little bit, and then we'll go to some log functions. So exponential functions have a base, and they're written as f of x equals a to the x, where a is the base, and we typically say a is greater than 0, it's positive. A isn't 1, because if a is 1, then that means it's the same number, right? 1 raised to anything is still 1, which means it's not going to grow exponentially or decay exponentially, it's just going to stay constant. That's the constant function. And x can be any real number. And we remember the notation for that, the little like e looking thing means is an element of, and the fancy r means the set of real numbers. If we think about the graph of this, so for the purposes of these graphs, we're going to keep a always positive, and technically a is always greater than 0, but we're also going to make it greater than 1 on these graphs and change the growth or decay based on the exponent. Now there are two ways to change it, and so we'll look at what that means. So on this first one, we'll do a to the x, where a is bigger than 1. And in that case, your graph looks like this. And so it's going to go up, grow exponentially. The domain of this graph is all real numbers, negative infinity to infinity. The range is from 0 to infinity, because it doesn't go negative. It doesn't touch 0 either. The y-intercept is at 0, 1. It's always increasing through the whole interval. It has an asymptote. That's the thing where it's getting really, really close to 0 but not touching it. And so y equals 0 is the asymptote. And it is a continuous graph through the whole thing. There's no breaks, there's no asymptotes that stop it, there's no holes. And so that's our growth with exponential graphs. We can also do decay where with a to the negative x. And that one looks like this. Again, it shouldn't touch the 0. Very similar domain and range. Right, y-intercept is still 0, 1. In this case, it's decreasing always instead of increasing. Still has the same asymptote, and it still is continuous. So 2 ways to make growth and decay. One way is look at the exponent. If the exponent is positive or negative, as long as your base is greater than 1, that's going to shift positive to negative. The other way is if we say a to the x is growth. For decay, we can go 1 over a to the x, right? That's the same as a to the negative x. So sometimes you'll see graphs like that, where, for example, 2 to the x and 2 to the negative x, or you could make this 1/2 to the x, and that would be the same graph. The textbook goes with a always being bigger than 1, so it's going to be like this. The exponent is going to have to become negative to make it a decay graph, rather than the base becoming something between 0 and 1. But both ways work, and so I don't know, depending on what you did in Algebra 2 and Algebra 2 Trig, you might have seen it the other way. So that's a general exponential graph. We also have a special base, so we're talking about this in terms of base A, but usually we kind of standardize things. So we use this base called E, which is known as the natural base. And this comes out of, well, you can kind of think of this in 2 ways. So one way is if we take the function 1 plus 1 over x raised to the x, and I want its limit when x goes to infinity, this evaluates to the value of e, which is about 2.718. Or if we did limit as x approaches 0 of 1 plus x to the 1 over x, that also equals e. So this is the definition of the e value. But you might be thinking, like, why would you have 1 plus 1 over x or 1 plus x to the 1 over x? Like, where does that come from? Well, so we can think about this in terms of an application of exponential functions. So if we think about exponential growth and decay as the things that we model with these functions, compound interest is something that comes up a lot. So with compound interest, we have a formula that tells us that if we take, so generally with growth and decay, we have some initial value times a growth factor, a growth multiplier, raised to the exponent will give us a final amount. Right, this works for any exponential growth or decay graph. In compound interest, our initial value is called the principal. That's how much we put in. The growth multiplier is our interest. And this is how many times we want the interest to get added on. The way that kind of works with compound interest is that we have a principal. And then interest rates are usually written in percentages. So for percentages, you need to add them to 1. Right? So if it's a 20% increase, that's really a 1.2 growth rate, because if you just did 0.2, that would actually make it go down. It's 100% of what you have plus 20%, so 1.2. Compounding just means that instead of adding interest only once at the end of the year, you'll add it multiple times at a fraction of the interest rate. So for example, if your interest rate for the whole year is 12%, but you want to compound it monthly, then every month they'll give you the 12% divided by 12. So they'll give you 1% every month, so that over the whole year they've given you 12%. But really they've given you more than that, because when you calculate 1% 12 times with different amounts that you're calculating on, you'll get a little bit more than if you just did 12% at the end of the year. So that's why compound interest is used more frequently. But based on that, we take the interest rate, we cut it by the fraction of how many times we're going to do it in a year. And then overall, in 1 year, we would have done it the number of times in that year times the number of years, right? So if in 1 year you did it monthly, you'd have 12 times 1, you'd have done it 12 times. So you get this formula for compound interest. And that's your compound interest formula, where A is the amount that you have at the end, P is the principal, R is the annual interest rate, N is the times you compound, and T is the number of years. So using this formula, we can kind of think about where does E come from? Well, so let's say we have $1. We have a really nice bank that's giving us 100% annual interest rate. And we get 1 year, because after this, the bank's going to go out of business. So if I try to plug all these numbers into my formula, I get principal of $1, 100% interest rate. I don't know what my number of times compounded is. And I'm going to do it, the number of times compounded times 1. Well, this is the 1 plus 1 over x over x. And now I want to get the most money out of it. So I want this x to be the biggest I can get. So we do limit x approaches infinity of this value. And that's when you end up with E at the end. So that's what E comes out from. It's like this maximum amount that you can get as a growth rate on these interest problems. Or like the maximum multiplier kind of thing. So E is usually like that standardized number we use. So let's do some practice problems with this. So the first one is looking at a bank account that has an interest rate of 1.5% annually. APR means annual percentage rate. Compounded daily. If I put in $5,000 today, how much money will I have in 40 years? So I want to just pick out all the information from this. My principal is $5,000. My interest rate is 1.5%, so that's 0.015. My time is 40 years. And the number of times compounded is daily, which means in 1 year I get 365 days. But we usually account for leap years as well. And to account for that, we're really just going to make this 365.25. That kind of follows like the reason we have leap years is because it takes a little bit more than a quarter-ish of a day more than 365 days to rotate around the sun. And so we just count up all those quarter days and add 1 extra day every 4 years. That's what we're kind of doing in this formula as well. We're just putting a 0.25, so every 4 years, that 0.25 will be a whole extra day. So now we can plug all of this into a formula. Right? So we do 5,000 initial value. And I want you to really think about these formulas, right? There's a formula for it, but really all it is doing is this initial value times growth multiplier to the x. You want to keep thinking of that because that will apply to any scenario you get, even if it's not an interest rate question, if it's not something that follows the format exactly, you'll still be able to solve the problem just using that basic concept of initial value and growth rate. So our initial value is $5,000, and we're going to put in an interest rate of 0.015 divided by 365.25 raised to the 365.25 times 40. And I don't have a calculator on me right now, so I would write that in your calculator, put it into your calculator, and you'll find what that equals. The next problem is another modeling kind of problem. So this one I want you to try on your own, and if you have questions, I can go over it in the live session. But again, we have a model given to you. You have this equation that tells you what the population growth is like. if we think about what's happening here, we have an initial value over here, and then we have its growth rate and version there. So this is a kind of modified version of an equation. So here we did initial value times growth multiplier. In this one, it's going to be initial times E, and then like a growth value goes up there. It's slightly different, but it's the same idea again. You can do it this way as well, where you know that the base is going to be E, so then you just like plug in some other value that you have, and you can solve for what this number should be. Usually that's called a K value, and you can solve for that, just like how you solve for like the A value in a parabola and stuff like that. I'm going to stop this video here to just make it a little shorter, and I'll do another video on logs.